This is the Spring 2017 final for MA 266. We're going through the entire thing and preferably as quickly as possible. Question 1. Let y of t be the solution to this initial value problem. We're looking for y at 2. So we're going to use integrating factor here, and we know that our integrating factor rho of t is equal to e to the integral of p of t dt, where p of t is the coefficient in terms of t attached to our y, as long as the coefficient on y prime is 1. So dividing this t out, we'll get y prime plus 1 over t y is equal to 3t minus 2 plus 2 over t. And this term over here is, this term here is q of t. We'll need that in a second as well. So this rho of t, we're taking the integral of p of t, that's the integral of 1 over t. We will get ln t, and e to the ln t is just t to the first power. So we can say that y of t is equal to 1 over rho of t times the integral of rho of t multiplied by q of t, which is just our right-hand side. So that ends up giving us 3t squared minus 2t plus 2 dt. And so y of t is equal to 1 over t times t cubed minus t squared plus 2t plus c. So now solving for the c value, we know that y at 1 is equal to 2, so 2 is equal to 1 times 1 minus 1 plus 2 plus c. Our 1 minus 1 will cancel out, and we're just left with c is equal to 0. So plugging that in, we are solving for y at 2. Y at 2 will be equal to 1/2 times 8 minus 4 plus 4, which gives us 4. So 1 is C. 2, let's find the solution to this initial value problem here. Well, this is a separable equation because we have some function of x on top and some function of y on the bottom. So we can rewrite this as 2y minus 4 multiplied by dy dx, and we can set that equal to 3x squared plus 4x minus 4. We can multiply our dx over to this side and take the integral of both sides, and we'll end up with y squared minus 4y is equal to x cubed plus 2x squared minus 4x plus c. Since y at 1 is equal to 3, we can solve for our c value here. Let's see, we'll have 9 minus 12, so negative 3 on this side is 1 plus 2 minus 4 plus c. So 3 minus 4, this is a negative 1, add 1 is negative 2, so c is negative 2, and it looks like E matches that exactly. 3, we have a salt tank problem to deal with. We know that the equation that we use every time for this is dq dt. Usually they call it q. Apparently this semester they chose to call it y, but I'm using q because that's what you'll see more often recently. dq dt plus r0 over v of t times q is equal to ri ci. Ri and Ci are the rate and concentration at which the salt water is entering the tank. Ro is the rate at which the fully mixed water, is leaving the tank. And then V of T is the expression for the volume of the tank as a function of time. And Q is our total amount of salt. So plugging in things, let's see. We have an initial condition up here. That's the first thing they tell us, that Q at 0 is equal to 10. We'll need that later. And we see that salt solution is flowing in at a rate of 4 gallons per minute and at a concentration of 1/2 pound per gallon. So RICI will be 2. Additionally, water is flowing out at a rate of 2 gallons per minute. So we'll replace that there. And since we start with 40 gallons of water, water is flowing in at a rate of 4 gallons per minute and out at a rate of 2 gallons per minute. We will gain 2 gallons for every minute or unit of t, that unit of time t that passes. So we can simplify things a little bit. This can be 1 over 20 plus t, and then we can apply the method of integrating factor. This is our q of t. We don't have to do anything. We don't have any terms over here to divide out. Here is our p of t. So our rho of t is e to the integral of p of t, which will just be e to the ln 20 plus t, or 20 plus t. So then q of t. Oh, yeah, having the q overlap with what we're calling q of t over here is maybe why they're using y, but we're gonna ignore that. So our amount of salt in our tank as a function of time is equal to 1 over p of t times the integral of p of t times this right-hand side here. So we get 40 plus 2t dt, and so q of t is equal to 1 over 20 plus t multiplied by 20t plus t squared plus c. Using our initial condition that q at 0 is equal to 10, we can say that 10 is equal to 1 over 20 times c. So c is 200, like that. And now finally we're solving for q at 20, right up there. And so q at 20 is just equal to 1 over 40 times 20 times 20, which is 400. 400. Oh, look at that. Haha. I integrated 40 and got 20t. This is 40t. So this is 800 here, plus 400 plus 200. We will get 1400 over 40, which simplifies down to 70 over 2, which is 35. So 3 is C. 4. If y of x is the solution to this differential equation here for x greater than 0 and y at 1 is equal to 2, then what is y at e? So for this, we're going to be performing the substitution v equals y over x, and you can rearrange this and then differentiate. You'll have to use the product rule, but you'll find that dy dx is equal to dv dx times x plus v. So we can go up here and replace everything, all of our y's with all of our y's and x's actually with v's. So our y prime, our dy dx, will become dv dx times x plus v, and then our right-hand side we have a y over x, that's a v, and x over y is 1 over v. We can subtract v from both sides and do a little rearranging. Let's multiply take 1 over all of our sides, so flip all of our fractions. We'll have v here, 1 over x, and dx over dv. Let's multiply that dv over dx and integrate both sides. And I should actually have the v. I'll move the v side over to the left. We'll have v squared over 2 is equal to ln x plus c. Multiplying both sides by 2, v squared is equal to 2 ln x plus, we'll call it c1. That's just a constant that's just equal to 2 times this c0. Sure. Taking the square root and noting that when we plug in 1 as an x value, we get a positive result. That means that v must be equal to the positive side of the plus or minus square root of 2 ln x plus c, replacing our v with y over x to undo the substitution. We see that y is equal to x times the square root of 2 ln x plus c. So plugging in y equals 1 here and setting that equal to, x equals 1, setting that equal to 2. 2 is equal to 1 times the square root of 2 ln 1, so that's 0, plus c. C must be equal to 4. So there is our formula right there. We are finding y at e. Y at e is just equal to e times the square root of 2 ln e plus 4. Ln e is 1, so we get 6 in here. And so e root 6, 4 should be c. 5. If the following differential equation is exact, select the implicit solution to this initial value problem. And if it's not exact, select not exact. So if a differential equation is exact, we have some expression m here and some expression n here, where m is by itself, n is multiplied by y prime, where m is the partial derivative with respect to x of some function psi. I'm pretty sure that's the letter psi. I really should look it up. And that n is the partial derivative of that function with respect to y. And because this is just a normal kind of function with sines and cosines and e's and everything, by Clairaut's theorem, the mixed partial derivative of this function, so the partial derivative with respect to y and then with respect to x, must be equal to the partial derivative of this with respect to x and then y. And as a result, if this is an exact equation, we should be able to take the partial derivative of m with respect to y and set it equal to the partial derivative of n with respect to x. And that relation should be true. And if it is, we can just do two relatively easy integrals and end up with a pretty easy answer. So finding my, that is negative e to the x cosine y minus, oh, I just integrated, didn't I? Yeah, sorry, this is a partial derivative, e to the x cosine y minus 2 sine x, and we're seeing if this is equal to nx, which is e to the x cosine y minus 2 sine x, and then that 2y term will just go to 0. So as a result, we know that this is an exact equation, and we can take the integral of m dy, m dx, and compare it to the integral of n dy, and we'll be able to find our function psi. So we're taking the integral of e to the x sine y minus 2y sine x dx, and comparing it to the integral of e to the x cosine y plus 2 cosine x plus 2y dy. Here we will get e to the x sine y plus 2y cosine x, and on the other side we get e to the x sine y plus 2y cosine x plus y squared. So these overlapping terms will only count once, and so we can say that psi of x y is equal to e to the x sine y plus 2y cosine x plus y squared. And feel free to stop and take the partial derivatives of this with respect to x and y, and you'll see that we get exactly m and n over there. So this, however, is not our answer, though, because we need and I'm going to need more space here somewhere, we need to apply this initial condition and recognize that the solution is not this psi, but it's this psi equal to some constant c. So we can say that e to the x sine y plus 2y cosine x plus y squared is equal to c. And really, if you want to be technical about it, we already know that the answer is c because that's the only left-hand side that matches. But if we plug in y at 0 is equal to pi, if we plug in y at 0 is equal to pi, what do we get here? We will get 0 plus 2 pi times 1 plus pi squared. And there's your 2 pi plus pi squared. So 5 is c. 6. Which of the following statements is true about the equilibrium solutions of this autonomous equation? So let's make a number line down here and put down all of the values for which dy dt is equal to 0. So this is true for y at 0, y at 3, and y at -3. If we plug in a value for y less than -3, let's say we plug in -10, let's see, we will have -10 times 9 minus -10 squared, which is just minus 100. So we have a negative times a negative, and so our derivative will be positive. So any solution curves that start below -3 will flow up as time goes to infinity to asymptotically approach 3. Let's see, what about t is equal to -1? For that, we can see that our dy dt will be -1 times 9 minus 1, which gives us a negative derivative. For y is equal to 1, we will get 1 times 9 minus 1, that's a positive derivative. And for y greater than 3, we would get like 4 times 9 minus 16, so that's another negative right there. And so we would characterize these solutions by saying that -3 and 3 are asymptotically stable, as if you start in their vicinity, in their kind of zones of control here, solutions will flow towards 3 and -3, but 0 is unstable because solutions will flow away from 0 as time increases. So A is our correct answer for 6. 7. Let's use Euler's method to find the approximate value of y at 0.2 for the following initial value problem with step size h of 0.1. So knowing that y at 0 is equal to 1, we can approximate y at 0.1 going up by 1 step size. We can approximate that as y at 0, which is 1, plus our step size of 0.1 multiplied by y prime evaluated at our most recent known approximation, or in this case, initial value. So this is y squared plus t squared. For t is equal to 0, y is equal to 1. So we will get 1.1. So y at 0.1 is approximately equal to 1.1. This is the new condition we're working with. As we approximate y at 0.2, that will be y at 0.1 plus our step size 0.1 multiplied by y prime evaluated here. So t squared will be 0.01, and 1.1 squared is 1.21. So adding these together, we get 1.22 in here multiplied by 0.1. We get 0.122, so this is 1.222. So E is our answer for number 7. 8. The largest interval in which the solution to this initial value problem is guaranteed to exist by the existence and uniqueness theorem is what? So in order to determine where we have, undefined behavior, we have to make sure that the coefficient on our y double prime is 1. So dividing that out, we get y double prime plus t minus 4 over 5 minus t times y prime plus 2 over 5 minus t times y is equal to ln t divided by 5 minus t. The discontinuities that we have for any of these expressions, so anything connected to y prime y or the constant on the right side, our discontinuities are for t is equal to 5 and t is less than 0 less than or equal to 0 because our ln t on our right side will be undefined there. But because our initial condition is for y at 7, if we draw a number line with these discontinuities on it, so we have 5 and 0, all of this is bad. The individual points at 0 and 5 are bad, but because our initial condition is at 7, we can go all the way from 5 to infinity without worrying about any of those discontinuities. So 8 is E. 9. Given that the function y1 equals t is a solution to this differential equation, we're choosing yt such that the pair form a set of fundamental solutions to the differential equation above. So we're going to be using reduction of order, that's what it's called, to find our second solution. Reduction of order says that y2 of t is equal to the integral of e to the negative integral of p of t dt, all divided by y1 of t squared dt, and then can't forget we have y1 of t outside there. So this p of t term is just the coefficient on y prime so long as the coefficient on y double prime is equal to 1. So we can rewrite this equation as y double prime minus 1 over t y prime plus 1 over t squared y is equal to 0. And so really we're taking the integral of negative 1 over t in here, so this is ln t. This will simplify down to t, and our y1s we can just replace with t's. So in the end, this is 1 over t in here, and we get ln t as a result. So B is our solution for number 9. Which of the following is a particular solution to this differential equation here? So we're going to be using the method of variation of parameters, and it's a little different from most variation of parameters questions in that they're not directly giving us our fundamental solutions, aka our solutions to the characteristic equation. So we need to find those ourselves. So finding our characteristic polynomial, that's r squared plus 4 is equal to 0, or r is equal to plus or minus 2i. So we can say that yc is c1 cosine 2t plus c2 sine 2t. And these are our fundamental solutions. We'll call this one y1 and this one y2. Variation of parameters says that yp of t, our particular solution, is negative y1 times the integral of y2 of t sine 2t multiplied by this right-hand side term here. We'll call that f of t, so long as the coefficient on y double prime is equal to 1. So that's times, I'll just put that in the denominator, cosine 2t. And then on the bottom, we're also multiplying by the Wronskian of our two solutions. That's the determinant of the matrix formed by our two solutions, cosine 2t, sine 2t, and their determinants. So that's negative 2 sine 2t and 2 cosine 2t. We'll see that this determinant gives us 2 cosine 2t squared plus 2 sine 2t squared, so that's just equal to 2. Replace that down there. And then this is only half of our equation that we have to solve. Next we have plus y2 of t. That's sine 2t, and I'm not going to have enough space down here, so we'll move this over. Plus sine 2t times the integral of y1 of t, which is cosine 2t, over our Wronskian, which is just 2, and then we also have to multiply by f of t up top, but that's just 1 over cosine 2t dt. So this simplifies our lives a lot because this will just be 1 over 2 here. So this integral will give us 1 over 2 t times sine 2t. And at this point we actually already know our answer because that's the only one that agrees with that term there. But we can do our u substitution over here and get a normal answer. Get the entire answer. So if we set u to be cosine of 2t, du is equal to negative 2 sine 2t. That means when we perform our u substitution, this will become negative cosine 2t times the integral of 1 over negative 4 u du. And working through all of this, we will get cosine 2t, 1/4 cosine 2t times the natural log of u, which is cosine 2t. So adding this with the bit that we already had, we get exactly answer choice D for number 10. I have to erase this. There we go. In an electric circuit, a capacitor and an inductor are connected in series. The charge Q of t in the capacitor satisfies this differential equation here with some initial conditions. If we are writing Q of t in that form there, then we need to find capital R, which is the amplitude of the motion, and delta, which is what we would call the phase angle, which we know to be the arctangent of B over A. And where is this B over A coming from? Well, we will eventually solve this and see that Q of t is equal to A cosine t plus B sine t. And there could be coefficients in here too in front of the t's. That's also possible. So that's arctan of B over A. This is our delta, and our R, the amplitude, is A squared plus B squared. So the magnitude of A and B. So finding these, all we have to do is solve our characteristic equation. 9r squared plus 1 is equal to 0. So R is equal to plus or minus 1/3 I. We can go plug that in to Q of t. So Q of t is equal to C1, and I'll use A and B actually. A cosine 1/3 t plus B sine 1/3 t. Finding Q prime of t will give us negative 1/3 A sine 1/3 t plus 1/3 B cosine 1/3 t. And from here, we can use the fact that Q at 0 is equal to 1. Q at 0 is equal to 1, and that will be equal to A, because our sine term will go to 0 and our cosine term will go to 1A. And then solving Q prime at 0, q prime at 0, we see that that's equal to 1, and this is 1/3 b. So b is equal to 3. We can go up here and replace those and solve for our two quantities that we're looking for. Delta will be the arctangent of b over a. That gives us an arctangent of 3. And then r is just the root of 9 plus 1, so root 10. There are more complicated rules involved in figuring out what this term delta is, the phase angle. For example, if your initial values are in a, I think it's dependent on what quadrant your solution is starting in, and there's a page in the textbook. It's under 3.6. It's like vibrations and resonance or whatever. Go look at that if you want to go memorize that. But I don't I don't particularly want to, and I haven't. So there we go. 11 is B. 12. A particular solution of this equation is in what form? Well, let's write out what we would like our guess to be if we didn't have any overlap with our characteristic solution. So because we have some constant times cosine, ypg, our guess for our y particular of t would be a cosine t plus b sine t, and then our 2e to the negative t would just be plus c e to the negative t, and then we have to split up this polynomial with negative 5t into plus dt plus e. And so this is what we would like it to be. But let's go solve our characteristic equation to see what that solution will look like. So that'll tell us what up here we have to multiply by t, or even multiple t's. So r to the fourth plus 2r squared plus 1 is equal to 0. R squared plus 1 squared is equal to 0. This gives us r equals plus or minus I with a multiplicity of 2. That means that we can write our y c of t as c1t cosine t plus c2t sine t. And remember that extra t multiplied in is coming from the fact that we have a multiplicity of 2 for those solutions. So now we've run into a very niche situation that I've never seen happen elsewhere, and I'm still not completely sure why this works out the way that it does. But in order for our guess to be valid, we end up having to multiply our sine and cosine terms by t squared. I think it might have something to do with the fact that if we expand the sine and cosine term like we would to make a guess about a particular solution, this would end up being at plus b cosine t plus ct plus d sine t, and we would have overlap so long as the exponent on our t and the sine and cosine up in our particular solution guess is less than 2. But I'm still not particularly sure why this works the way that it does. That said, and reiterating, I've never seen this happen elsewhere. Usually the undetermined coefficient questions that we get don't work like this, and they're generally much simpler to think about. So I wouldn't particularly worry. I've tried to look into it, Googling around, but I haven't yet come across an example question that actually goes through why this is the case. Please comment, text me, email me. I don't know. I was gonna say tape a picture to my dorm room, but not there anymore. That's kind of sad. Just let me know why this works the way it does, if you think you know. But that leads us to option D as our solution for 12. 13. A spring system with an external forcing term is represented by this equation. The steady state solution, we should read this as yp of t, is given by what? So if we're looking for yp of t, which is the solution that kind of takes control more and more as time goes on, that is going to be given by solving for our undetermined coefficients. We would like our guess for y particular to be a cosine t plus b sine t, just generalizing what we see over here. But if the roots of our characteristic equation are either, well, there's no either, if they just are plus or minus I, then we have an issue. So let's see if they are. R squared plus 2r plus 2 is equal to 0. R plus 1 squared is equal to 0. So r is equal to negative 1 with a multiplicity of 2, which is great news for us because it means that this is a valid guess. Finding ypg prime of t gives us negative a sine t plus b cosine t, and y double prime gives us negative a cosine t minus b sine t. Plugging these into our primes up here, we get negative a cosine t minus b sine t minus 2a sine t plus 2b cosine t plus 2a cosine t plus 2b sine t is equal to 4 cosine t plus 2 sine t. Okay, isn't that a lot of fun? So let's collect all of our cosine terms. We will have negative a plus 2b plus 2a is equal to the cosine over here, which is just 4. And then our sine terms, negative b minus 2a plus 2b is equal to 2. Combining like terms over here, we will just we'll get a positive a there and a positive b here. We can make this into a matrix: 1, 2, 4, negative 2, 1, 2. Adding 2 row 1s to row 2, we'll get 0, 5, 10, so we can simplify this down to 1, 2, and then subtracting, we see that b is equal to 2 and a is equal to 0. So replacing that way up here, we get 2 sine t. So a is our solution for 13. Let's find the inverse Laplace transform of f of s given right here. We'll need to do a pretty painful partial fraction, but we'll see that this is equal to a over, I'm using alpha plus 2 plus b alpha plus c over alpha squared plus 2 alpha plus 5. Multiplying this entire denominator up into everything, we get a alpha squared plus 2a alpha plus 5a plus b, and I'll sort this a little better, b alpha squared plus 2b alpha plus c alpha plus 2c, and this is equal to 2 alpha squared plus 5 alpha plus 7. So setting our corresponding terms equal, we'll see that 5a plus 0b plus 2c is equal to 7. Additionally, that 2a plus 2b plus 1c is equal to 5, and that a plus b plus 0c is equal to 2. And let's solve this matrix. Subtracting 2 row 3s from row 2, we will get 0, 0, and 1 here. we can use that to make this 0, 5, simplifying this down to 1, 1, and subtracting. Oh, would you look at that? We get 1, 1, and 1. So moving that over a little bit, I'm going to grab my table too, which we'll need in a second, and we can plug these a, b, and c values in, and we should be able to directly take our Laplace transform, inverse Laplace transform. So we have 1 over alpha plus 2 plus alpha plus 1 over alpha squared plus 2 alpha plus 5, but that's one of our kind of magical ones because we can replace that with alpha plus 1 squared plus 2 squared. And we'll see that the inverse Laplace transform of alpha minus a, where in our case a is negative 1 over alpha minus negative 1 squared plus 2 squared, so b is 2, is, this will give us e to the negative t, negative 1t times the cosine of 2t. And then this guy, that's the first one that we kind of learned. The inverse Laplace transform of 1 over alpha minus negative 2 is e to the negative 2, e to the negative 2t. And so that should be our answer. We get B for 14. Let's find the Laplace transform of this function here. This is the last question on all of the finals from the past 3 years for both MA 265 and 266 that I did not have figured out. As in, I did not know why the correct answer was correct. Like I did not know how to do this one. And about 20 minutes ago, no, way more than that, like an hour and a half, I figured it out. So let's see if we can replicate this. So we have a function, a piecewise function, where from t between 0 and 1, our function is equal to 0, and then it's equal to t e to the t. So I'm assuming that's going to be some, big jump like that. But we can express this relatively easily using the power of, what are they called? Unit step functions. So uc of t is a unit step function that is equal to 0 for all t less than c, and is equal to 1 for all t greater than or equal to c. So what we can say is u1 of t times t e to the t is equal to f of t, because for t between 0 and 0.9999999, this function evaluates to 0, and then elsewhere it evaluates to, or elsewhere to the right, it evaluates to t e to the t. The issue with this is that we don't currently have it in the form that 13 likes, where we have uc of t and then times some function where all of our t's are replaced with t minus c's. But we can quickly fix that. We can rewrite f of t as e to the t times u1 of t multiplied by t minus 1, which is what we want. But in subtracting 1 there, we'll need to add u1 of t, like that. And just checking to make sure that this works out. Yep, that should be good. So we know that the Laplace transform of anything multiplied by e to the some factor of t, all we have to do to take that Laplace transform is ignore it for the time being, take the Laplace transform of everything else, and then replace all of our t's with all of our s's with t minus whatever is multiplied by t up here. So in our case, all we have to remember is at the end, when we have our f of alpha, replace all of our s's or alphas, whatever you want to call them, with t minus 1. So that leaves us the task of taking the Laplace transform of u1 of t times f of t, well, not f of t minus 1, f of t equals t, so f of t minus 1 is this guy right here. And because f of t is equal to t, and we're just taking the Laplace transform of that t, we get e to the negative 1 alpha multiplied by the Laplace transform of t, which is 1 over alpha squared. And then to this, we're adding the Laplace transform of u1 of t, which just gives us e to the negative alpha over alpha. But we have to remember, all of our alphas are being replaced with alpha minus 1s. So alpha minus 1 will become alpha plus 1 up here, plus 1, alpha minus 1 squared, and alpha minus 1. And so that gives us answer choice B if we replace all of our alphas with s's for 15. If y of t is the solution to this initial value problem, what is y of t? We have a delta function over here, which we know how to take the Laplace transform of, so we can just take the Laplace transform of both sides. I guess I will. I'll do it, whatever. The Laplace transform of y double prime in general is alpha squared y subscript alpha minus y0 times alpha minus y prime at 0. Whereas the Laplace transform of y prime is just alpha minus y0, and the Laplace transform of y is just y subscript alpha. But since both of our initial conditions here, y at 0 and y prime at 0, are equal to 0, we can ignore these terms for now. So taking the Laplace transform of both sides of our equation, we will get alpha squared y alpha plus 2 alpha y alpha minus 15 y alpha, and we can set that equal to, let's see, the Laplace transform of delta at t minus 1 is e to the negative 1 alpha. So factoring out a y alpha and dividing it, we'll see that y alpha is equal to e to the negative alpha multiplied by 1 over alpha squared plus 2 alpha minus 15, which we can factor to alpha plus 5, alpha minus 3. And if we can do a quick little partial fraction on this, we should be good to go. And we'll have everything in a form that we can deal with. And I think I'm actually going to go down here to do it. A over alpha plus 5 plus b over alpha minus 3 is equal to 1 over alpha plus 5 times alpha minus 3, multiplying that denominator up. A alpha minus 3a plus b alpha plus 5b is equal to 1. Therefore, negative 3a plus 5b is equal to 1, and a is equal to negative b. Replacing these 3a's, these negative 3a's with, well, you know what I mean. We're replacing this a with a negative b, so we'll get 3b, so 8b, b is 1 over 8, a is negative 1 over 8. A is negative 1 over 8. So we get negative 1 over 8 times 1 over alpha plus 5 plus 1 over 8 times 1 over alpha minus 3. There we go. And all of this is then still multiplied by e to the negative alpha. I'm going to factor out this 8, and we are good to go because the inverse Laplace transform, what am I looking for? Yeah, the inverse Laplace transform of e to the negative cs times f of s will just give us uc of t, so we will get our inverse Laplace transform of f of alpha. We will get 1/8 because that factor doesn't change at all. uc of t for c is equal to 1, so u1 of t multiplied by the inverse Laplace transform of this thing, replacing all of the t's that we get with t minus c. So we will get negative e to the negative 5 t minus 1 plus e to the 3 t minus 1. And looking around here, looks like e is exactly what we are looking for. Oh, I almost forgot to do this question because we ran over its space. Let's find the Laplace transform of this integral expression right here. We know that anything, the Laplace transform of anything multiplied by e to the t will just be the normal Laplace transform of whatever you're multiplying by e to the t, as long as you replace all of your s's, in our case alphas, with alpha minus c. And then we know that the Laplace transform of this whole bit that's multiplied by e to the t will just be the Laplace transform of f of t, where f of t is this guy right here. Our f of t is cosine of t minus tau, but we'll remove that minus tau, so cosine of t. Because you can take this, replace all of your t's with t minus taus, and you get our f of t minus tau up there. And then g of t is just this g of tau here, so we'll replace that tau with a t. We will get sine of t. And so we're taking the Laplace transforms of each of these individually and multiplying them together, and then replacing all of our s's with s's minus 1. So the Laplace transform of cosine t is alpha over alpha squared plus 1, and the Laplace transform of sine of t is 1 over alpha squared plus 1. Multiplying these together and replacing all of our alphas with alpha minus 1s, we get alpha minus 1 over alpha minus 1 squared plus 1 squared. And so A is our answer for 17. 18, let's consider this system. Oh, look, we can get rid of those. Let's find all the values of alpha such that the origin is an asymptotically unstable spiral point. So those are a lot of adjectives altogether. Really what that means is that we're looking for eigenvalues with a positive real portion and then a conjugate imaginary portion on top of that. So the imaginary portion is contributing the spiraling behavior, whereas the positive real portion means that solutions will be pushed farther and farther away from the origin as time approaches infinity. So looking for this is just equivalent to solving for our eigenvalues and then just looking at what alpha could be. So we're solving negative lambda times alpha minus lambda plus 16 is equal to 0, lambda squared minus alpha lambda plus 16 is equal to 0, and solving for lambda, we will get negative b over 2, so alpha over 2 plus or minus the square root of b squared minus 4ac, all divided by 2. So as long as alpha is greater than 0, we will have the real portion here that we're, the positive real portion here that we're looking for, and as long as alpha is less than 8, the portion under this square root will be negative. So alpha between 0 and 8 is our answer D for 18. Let x of t be the solution to this initial value problem. We're looking for x at 1. Finding our eigenvalues is 3 minus lambda, negative 1 minus lambda, plus 4 is equal to 0. Lambda squared minus 2 lambda minus 3 plus 4 is plus 1 is equal to 0. Lambda minus 1 squared is equal to 0, so lambda is equal to 1 with a multiplicity of 2. So that complicates our life a little bit because we're going to need to find a generalized eigenvector eventually. But let's just solve a minus lambda I and see what eigenvector we get. So for lambda equals 1, we get 2, 1, negative 2, negative 4. We can simplify this down to 1, negative 2, 0, 0. And we get an eigenvector. We get an eigenvector of 2, 1 out of it. Because we can say that x1 is equal to 2, x2, and since x2 is our free variable, if we're expressing a vector in terms of x2, x2 is equal to 2x2 is equal to x1, and x2 is equal to 1 of itself. So there's our eigenvector. So we can start setting up our solution, x of t, as c1 v1 e to the lambda 1t, lambda being 1, so t, plus c2 v1 multiplied by t, plus our generalized eigenvector, times e to the same lambda t. Finding this generalized eigenvector involves setting a minus lambda I, so that's 2, 1, negative 4, negative 2, equal to our first eigenvector, 2, 1. And solving it, and I'll show you what we're up to here. It's a little bit weird. We can divide row 1 by 2, 1, negative 2, 1, and use it to set row 2 equal to 0. And what we're doing now is looking and noticing that these 4 terms, our 4 entries on the left, are the same as the 4 terms that we used to end up solving for our first eigenvector. And as long as this is true, we can just take the right-hand side here to be our generalized eigenvector, like so. Solving for c1 and c2 involves plugging in x at 0 is equal to 1, 0. So 1, 0 is equal to c1 times 2, 1 plus c2 times, well, this term will go to 0, and we're just left with 1, 0. Solving the matrix associated with this, we have 2, 1, 1, 0, 1, 0. And we see that c2 is equal to 1 and c1 is equal to 0. So we can get rid of this entirely. And what are we doing? We're looking for x. We're looking for x at 1. X at 1 will just be, let's see, did I? No, I don't think I messed anything up. X at 1 will be 2, 1 plus 1, 0, so 3, 1 times e. And 3, 1 times e is 3e over e, so 19 is a. 20, let phi of t be given there, and let it be the fundamental matrix of this homogeneous system. We're looking for the particular solution to this non-homogeneous system. So the equation that we're going to be solving here is xp of t is equal to phi of t times the integral of phi negative 1, phi inverse of t, multiplied by f of t, which is our f of t term here, the bit that makes everything non-homogeneous, f of t dt. And if we solve this, we should be on the right track. And wait, I need to go make sure this is right. Okay, we're good. This should be correct. Let's start plugging some things in and solving. Let's find the inverse of phi of t. That will be 1 over the determinant, which is e to the 4t, e to the 4t plus e to the 4t, so 2e to the 4t multiplied by switching the a and d positions, e to the 3t, e to the t, and changing the sign on the b and c positions, e to the t negative e to the 3t. Multiplying this 2e to the 4t in, Actually, I don't want to do that yet. Let's multiply by f of t and then simplify everything down to take our integral. Our f of t term is just right here. That's 0 for e to the t, and this will give us 1 over 2 e to the 4t multiplied by, well, we have a 2 by 2 matrix and a 2 by 1 matrix, so we'll get another 2 by 1 matrix as an output. Let's see, we will get negative 4 e to the 4t and 4 e to the 2t. So dividing that 2e to the 4t out, we get negative 2 and 2e to the negative 2t. So now we're taking the integral of this and we're going to multiply that result by our fundamental matrix and we will have a solution. So this integrated, and we're, for whatever reason, not caring about the c's and any constants that we get from this integration, we get negative 2t and negative e to the negative 2t. That works, right? Yeah, that looks good. Okay, we are, as our final step, multiplying by our fundamental matrix, which is e to the t, negative e to the t, e to the 3t, e to the 3t, and we will get a 2 by 1 matrix with, let's see, negative 2t e to the t minus e to the t, and on the bottom 2t e to the t minus e to the t, and we can factor out an e to the t, and we get negative 2t minus 1, 2t minus 1, e to the t, and this is our x particular. This is the only time they've made us do anything with fundamental matrices on a past final in the past couple of years, although given what I've seen on midterms this semester, I think it's perfectly reasonable to see both a matrix exponentiation question, so solving for e to the at, and also one like this where we have to actually apply the fundamental matrix to find a particular solution, or even there's another formula for a solution given a initial condition. So this xp matches up with option D, 420, and we are out of here. Hope this was helpful.